Okay, so for those people streaming online, I know you can't see the audience, but there are literally people hanging from the rafters. And it's also hard to hear what's not in the microphone, but I'll let you know every time there's applause, which I consider to be often. So what we're going to be doing is fitting a random forest in 5 minutes. This is actually not a misnomer. We will get through fitting a random forest in 5 minutes, but because I'm a very bad joke teller, the organization of this talk is going to go a little bit backwards. It's like, I'm going to tell you the punchline of the joke, and then we're going to work our way back through it so that you can understand what that punchline means. And just like any joke, when I start with the punchline, you may or may not understand it right at first, but hopefully by the end, they'll have that aha moment and realize that, you might understand random forests, but I'm still not particularly funny. And so I noticed some of you have computers and some of you don't. So those who have computers, I encourage you to type along with me. We're actually going to do a little bit of live coding, but it's not going to be so much that those without computers will feel abandoned. And just in case, I know maybe a couple of you know something, about Python. Maybe you have Anaconda installed or Python installed with some requisite packages. Maybe you have no idea the words coming out of my mouth, and that's okay, because what I encourage you to do, if you do have Python installed, and if you do have pandas installed and scikit-learn installed, and if those things make sense, then you can run on your local machine. But if not, we'll steal a little bit of a Python console. If you go to the URL pythonanywhere.com/try-ipython, you're actually brought to a console that you can type Python in. So if you want to join, and if you don't have all the stuff installed in your local computer, you can still join us in our typing just by going to this website and then typing here in the browser. And if not, don't worry. You can watch and learn and enjoy as well. So as you navigate to pythonanywhere.com, try IPython, just one more time. As you're navigating there, let me tell you what we're going to start with is we are going to create a classifier. What that means is that we have some data. We have some certain features, some attributes of iris flowers. There's 3 different subspecies of flowers. There's Setosa, Virginica, and versicolor is the 3 names of these different subspecies of iris. And the truth is, what we want to do is be able to identify which of the subspecies of iris that we have based on the measurements of their petals and their sepals. And because, even though I had used the data set many times, because it's sort of the quintessential classification data set that was put out in 1937 by one of the deities of statistics named Fisher. What happened is he created a data set 150 samples large of different irises, 50 of each of those 3 different classes of irises. And here's one of them. This is the versicolor iris. And just so you know, the longer of what I would call petals are not actually petals. These are the sepals. So there's a sepal length, the sepal width, and then the shorter ones are the petals. So there's a petal length and a petal width. And using those 4 features, the sepal length, sepal width, petal width, we're going to try to identify which of the irises we have, in our hand, which is the one that we have measured. Okay, and we can do this. Let's see the time. It's 7:11 right now, and I bet you that we can do this in under 5 minutes. Create a classifier that works quite well in IPython, and I will tell you the steps, and we can all type together. But we first have to get our hands on the data. So within your Python console, if you're on this website or if you're on your local machine, what we need to do is bring in a function that helps us load the data onto our machine. And so what we're going to do is type from sklearn.datasets import load_iris. Notice I'm joining you on the browser so that I can't cheat and already have my answers in front of me. Okay, just to note, scikit-learn is one of these, it's the popular kit on campus. It's the scientific kit for machine learning that Python has from it. And it has already collected many data sets for you to practice with. And so this is one of them, is the iris data set. And we're going to import that iris data set. I'm going to call it iris. I'm going to set iris equal to load iris, parentheses, in parentheses. And now within this object iris, within this variable iris, I have all the data set that Fisher made back in 1930s with the measurements and the details of which particular subspecies of iris we have, right? Oh, look, I haven't cheated yet. Now, if I was to try to describe iris to you, I don't have to, because fortunately, inside that iris data set, it also has some information about it. It tells you what the 4 features are that we already covered. And it gives you some of the basic descriptive statistics of those iris data sets. But we're going to look a little bit deeper into that in a minute. First, let's actually create a random forest classifier and see how well it works. I see a picture being taken. Okay. All right. And by the way, it's 7:14. I've got what, a couple more minutes here before I am out of my 5 minutes. So again, from the scientific kit for machine learning, from the module ensemble, I'm going to import random forest classifier. Okay, and you may or may not believe me, but we're actually almost done making our classifier at this point. I need to make an initial instance of this random forest classifier. So I'll call it, say, RFC, name it what you like, but this seems to be good. And we could just in parentheses here and everything would go okay. But just because we're going to have a little bit more of a discussion later, I'm going to write in one parameter that's called in estimators. I'm going to set that equal to 100. And just so that you don't get too frustrated if you don't know exactly what all these pieces are doing, a forest is named a forest because it's made of trees. And a random forest classifier is also itself made of trees. And so in estimators here is just telling me how many trees I want in my forest. And I'm saying I want 100 trees in my forest. This is actually going to be the default number of trees that the random forest classifier has on the next iteration of scikit-learn. Okay, let's see, how much time do I have? All right, I have 1 minute. So what I'm going to do is rfc.fit. I'm going to type iris.data and iris.target and hit enter. And guess what? I just created a random forest classifier. We did it in under 5 minutes. I should have said 4 minutes. We still could have had the alliteration with the Fs, but I wanted to give myself some leeway. So I know this might not be as climatic as you had hoped yet, but we will get there. What happened in this was we began an instance of the random forest classifier. So in the background, there's algorithms that know how to create a random forest. And what we fed it was, here is the collection of measurements that we made of the sepal length, sepal width, petal width. And then what we're trying to guess with those 4 features is our target, which type of iris it is. So this is the setosa, virginica, or versicolor. And what it does is it sees, using the random forest algorithm, if we can distill some structure from the iris data, from these measurements, to infer the correct target value. And now we can even check how well we've done, right? So here's what we're going to do. We're going to look at the accuracy of our classifier on the set that we just trained it on. That's cheating a little bit if you've seen something about like train test splitting. If not, we'll talk about it later, no worries. But here's what we're going to do. I'm going to re-input the data and the target. And what it's going to tell me is the ratio of the number of correct answers it got over the total number of answers. Right? So it could have, say, guessed 98 out of 100 correct. Well, then it would have a 0.98% accuracy. It could have guessed 2 out of 100 correct, and it would have a 2% accuracy. So we're looking for some number close to 1. And in fact, it does perfect. Now, this is for a couple reasons. One is that this is an extremely, extremely cultivated and and nicely put together data set that is used all the time for classification, because you almost always get satisfactory results, because these classes are so far apart that even if I just sort of plotted the difference in the sepal lengths and sepal widths, it'd be very easy to see how to classify it. And if it's easy for you to see how to classify it, it's also typically easy for the computer to see how to classify it. Okay, so we did quite well. It could be overfit. Don't worry if that word is not yet in the vernacular, because we will eventually talk about that today. But nonetheless, here in a browser, using very little time, we were able to create a random forest classifier. You can too. And that's sort of the punchline of the whole talk today. And so we're going to go back now and piece apart this random forest classifier underneath. We're going to break it apart into its trees, how it combines its trees, and what it's actually doing, so that when we come back together here, you'll understand a little bit more about what happens when I hit fit this random forest. What happens when I'm actually using this algorithm to create the classifier that's going on in the background. And just as a complete side note, there is many say videos online about creating random forests, and everybody has their own take. I have my own take. But what's nice about you being here with us and with me today is you're free to ask questions, right? The interactivity here is the edge that you have by being here, by asking questions, or if you're online, by potentially sending me an email. If you know my email address, I don't know if they have that on the slides, but I feel like maybe I'll get somewhere between 0 and 5 emails after this. Nonetheless, feel free to interrupt me. Feel free to raise your hand. I try to, I took a education course, so I know to look out and make eye contact, and so I'll see if your hands are raised. And we can discuss, we can go deeper. This is totally curated for you guys. This is made for you. So ask me questions along the way and we'll get there. But so far, we've created a random forest classifier, and at least on the data set that we looked at, we did quite well. Okay. So look, without cheating, I was able to reproduce exactly what I have here in my cheat sheet. So let's discuss exactly what I talked about just a little bit more in detail, so that you can get a little bit more familiar with this data, so that when I start piecing things apart and telling you about decision trees, it all works out well. Now, you don't have to type along with me at this point. You can try and probably succeed if you can type as fast as I can talk, which seems to be quite fast according to my student evaluations. But what we will do is we will sort of investigate the data that we put into it, just so you can get a little bit more of a feel for it. And then we will look at each of the pieces of the random forest and how it puts together the estimation that it does. So one of the, again, the popular kid on campus in Python for doing data wrangling, and in particular for looking at, say, data tables and two-dimensional objects of data, is pandas. This is, not named after the animal, just like Python is actually not named after the animal directly. It's named after Monty Python, the skits of British comedy. This is actually panel data, is where pandas comes from. And what I'm going to do is I'm going to take that iris data. This is the sepal length, sepal width, petal length, width measurements, and I'm going to throw it into one of these pandas data frames, and I'm going to just investigate it. So I take my iris data, I name them with what they're named after, what the features actually are doing, what they're describing. I put them into a pandas data frame, and I'm just going to call this X for the time being. And similarly with the target, remember, here's the measurements, but here's our goal. Our goal is to understand what type of iris it is. So the target tells us what we want to classify as, and the data is telling us what the measurements we are using to try to guess that classification. So here, X is going to be that data that we're going to try to use to infer what Y is, and Y is going to be our goal, our target, right? And so from the iris.target, I'm going to put that into a data frame. I'm just going to give it some column name. And because I know it's a numeric value, just because I already looked at the data, I'm going to call that column name iris num type. Okay. Now, scrolling down, one nice thing about pandas data frames is that you're able to very quickly look at them in a sort of visually stunningly nice way. So if I look at the, say, 5 rows randomly sampled from my data frame X, from my data that I have put together, again, you can see that maybe I wasn't completely lying to you about what each of these columns represent. So in centimeters, this is telling you the sepal lengths, the sepal widths, the petal length and the petal widths, and each of the rows represents one sample, one specific iris flower that Fisher or one of his subordinates was measuring so that they could put together this data table. Right? And so I want you to pay attention. Here's these numbers here. What do they represent? These are just the index. It's just some numbering along the columns to identify, or along the rows, just to identify which number row it is. So since I took a random sample of 5 rows here, this is the 26th row, the 71st row, and so on. So those numbers are just to tell you where they land within that data frame. If I do the same with Y and I take a random sample, not so random because I actually want it to match up with X, my data, just so that we can compare. I still am taking the 26th row, the 71st row, 99th row, and we can look around. So with the sepal length, sepal width, petal width of these values, that was a setosa type iris. Compared to if I have sepal length 6.1, sepal width 2.8, petal length 4.0, and petal width 1.3, that one was a versicolor iris. Yes?
You were able to guarantee that you were going to get the same random rows using the random state approach?
That's correct. So the question is, how did I guarantee if I randomly sampled that I was going to get the same random sample? And the way I did that was in my sample call here with the pandas data frame, I set the same random state. And how did I pick this random state? Well, today is December 11th, I think, right? So I just chose 1211 arbitrarily, but as long as this number, 1211, agrees with this number, 1211, then I'm guaranteeing that I'm starting, this random sample sort of starts at the same point and goes along. There's no such thing as true randomly generated numbers. We always, unfortunately, have to have some algorithm, some way to determine what it is. And the randomness comes from these seeds. So there's like a second label, like a second layer of randomness. You input a seed, and based on that seed, then it generates numbers that look random. So if I gave it 2 different seeds, then those number distributions would look quite different. But giving it the same seed, it sort of starts the rock dropping at the same point, and it will fall the same way, even that if as it's falling, it's a little bit jagged, that looks random. So yeah, by setting the random state within the sample to 1211, in both X and Y, I was guaranteed the same rows along the way. And just to note, I connected a method on here, sort index, because that random sample could, in fact, come out in any order, and I just wanted to make it 26, 71, 99, 109. I just wanted that to be ordered. So the sort values isn't doing anything effective, it's just making it look a little bit nicer so that we can read it, I don't know, a little bit easier. Okay, let me take a break here and ask if there are any questions at this point of what's going on. Yes? Here, with the pandas data frame. Yeah, so I'm scrolled up to the code lines above. While I'm here, just in case, just so that everybody has a chance to type, let me tell you a little bit more about what's going on here. In most coding languages, in Python and in R, there are ways to import extra libraries. So there's certain base functionality in all these languages. So just when you start up an instance of Python and start up an instance of R, there's certain base functionality that it has built in, right? You can add a plus sign. You can put 3 + 4, and you'll get 7, and you don't have to do anything special. But then a lot of objects you want, or a lot of methods or functions that you want it to do, aren't sort of built into the base, and so somebody else has to build a library that you have to tell it to use. And in Python, the way you tell them to use these libraries that aren't just built into the base functionality is through import. So here, forget this as PD for a second. I'm just saying I want to use this pandas library, this panel data library, and I'm going to do that by importing it. Now, I am lazy, and so I don't like to type pandas every time, so I'm going to give it a nickname. And the nickname I give it is PD. This is the common nickname. It's just an alias. But this really means I want to import pandas, but whenever I'm pulling something from pandas, I'm just going to refer to it as PD, so I don't have to keep typing pandas over and over again. Okay, so for example, when I set up X here as a data frame, I type PD instead of pandas.dataframe. This then will create my data frame from the iris data that we had before. and I can even name the columns. And fortunately, you know, in this Fisher iris data set, it also gives us the feature names, the column names along the way. And similar story with Y here. All right, are there other questions? There's 150. There's 150. There's 50 of each type. So there was 50 setosa, 50 virginica, and 50 versicolor, right? Well, actually, in this data set, there is 150 measurements. There are no more. So, you know, this was done back when you actually had to go out with a pencil and paper and write this down. So 150 back then was big data, whereas 150 billion now is big data, right? But this is 1930s big data. Up above? Ah. So yeah, so the question is what is happening here with this 100? Okay, so when we fit our random forest, I told you you can, but you don't have to type in this in estimators. Now, what's happening, this in estimators doesn't deal with the data set directly. It tells the algorithm one of the parameters that it needs to know to run the algorithm of random forest itself. And what happens in a random forest, which we will touch on later, but it's always good to talk about things many times, is you have a certain number of trees. And actually, each of these trees itself is a classifier. And then what I'm doing is I'm taking, in this case, 100 trees to make my forest. Each of these tree classifiers puts in a vote. This tree says it's setosa, this tree says it's setosa, this tree says it's virginica, this tree says it's setosa, and whichever class wins the vote of those, in this case, 100 trees, that's the one that my model will predict to be the correct value. So this 100 here, this in estimators here, is in fact the number of trees I want in the forest. The more trees I build, though, the longer it'll take to run because it has to make a new classifier, a new tree for each of those estimators. Yes. So the question is, what's a good standard? And 100 is a reasonable good number. How do I know that? Well, because the people that are working and keeping up scikit-learn are making it their default value, right? To a certain extent, you can add, you can put a lot of estimators in there. You can make a lot of trees in your forest at the cost of computational expense. It's going to take you a lot longer if you create a lot more trees. And so you have to make this balance. And one thing we can do, for example, is look at how our accuracy is changing based on the number of trees. And at some point, it probably is going to sort of balance off. It's not going to make much of a difference. And so then we choose the least number of trees where it stops making a difference. But there's not, 100 is sort of, if you just want to sort of put it into a vanilla random forest and try the best you can with just sort of out of the box behavior, 100 is a good number. But the truth is, if there was one right answer, then we would just use that all the time, right? And this is the beauty of sort of machine learning, is that there is no right answer. It's why data scientists are very marketable, because there's this art to it too. It's these parameters that you get to think about. You get to think about why I want to use this parameter. Why do I want 100 trees versus not 100 trees? And it's why two people can both be working on the same set of data, get quite different results. And it's because of sort of the principled artistry that's happening behind it in creating these models. Other questions? Yeah, these are excellent questions. Okay. So why? Okay, I got a question for myself. Why? No. Why do we care to make a model where I already know all the answers, right? I told you I knew what that target variable was. And this is actually, you need that to create the answers, because you need your algorithm to already know the answers to sort of try to find a structure from the data to the target. So why do we care? Well, we care because eventually we assume we're going to put in new samples. We're going to take measurements of different irises eventually, and then it's going to guess which iris type it is. So that way I don't have to do extra work. I just put in the data of measurements that I can get, and it outputs what it guesses as its target. So just real quick, just to show you how this works, I made up some phony numbers. You know, I have sepal length of 6, sepal width of 3, petal length of 5, and sepal width, or sorry, petal width of 2.5. And in that random forest classifier that I created, there's this predict method, which is arguably the most useful of the methods from the classifier that we made, because now we're able to apply our classifier to samples that we haven't seen before. I input that sample, and its guess is 2. Well, let me go back up and just remind us what 2 means. So it thinks that that sample is then Virginica. It guesses it's 2 because it's choosing its the numeric labeling of that particular type of flower, and in this case, Virginica. So I made up a sample, I put it in, so I went out into the wild, I grabbed this measurements, I want to know which of the irises it is so I can impress my friends, and it turns out it is Virginica according to my classifier, which may or may not be right, but my classifier seems pretty good, so I have some high confidence in it. All right. So we've done our random forest, we've predicted with it, we understand a little bit more of the structure now than before. So let's go back and let's look at individual trees. Remember, we said there was 100 trees in this random forest. That was the number of estimators that I threw into it. So let's look at individual trees. What are these individual trees and how do they work? And so this, I mean, it's a toy example because, you know, there's beer, and I should have put pie instead of cake, right? Because we're having pizza. But there's beer, wine, and pie outside, and it's like, how do you want a carb load tonight? Well, if you like beer, you follow this flow chart, and you'll drink a beer. If you don't like beer and you're thirsty, well, then you might drink wine, and if not, then you might eat our pizza, right? This is, I think, something that we are all pretty familiar with. We've seen flow charts before, right? It's just a series of yes or no questions, where at each yes or no question, we sort of restart our new yes or no questions, and we follow these branches down, and we just follow yes paths, right? So, well, not yes paths, we follow the correct answer path. So if we're yes here, then we go this way. If we're no here, we go this way. And this is what is happening in the trees at a very, you know, ridiculous level, where if I had 3 labels of my iris, but those labels were beer, wine, and cake instead, this gives me a way to go down and label them by saying, here's my sample. Does my sample want a beer? Then I'll label a beer. If it doesn't want a beer, is it thirsty? If it's thirsty, it's labeled wine. If it's not thirsty, it's labeled cake. So these flowcharts are common in our lives. They're, you know, I've seen them many times in memes, and so happens that they're extremely useful in statistics and machine learning as well. Okay, so going back in our memory, it was in estimators was the parameter that we set equal to 100. After our random forest has done its work, we hit dot fit, we entered its measurements, its data, and its target. It did all its work of the algorithm in the background. What it actually did was it fit 100 different decision trees. So that means every sample goes through one of these paths of yes or no's and finally gets assigned a label at the bottom of that decision tree. And I can access those decision trees in my random forest classifier by looking at its estimator's attribute in the RFC object here. For example, just to note, you know, I don't know, some people think ground floor should be labeled 1, and some people think ground floor should be labeled 0. Python thinks ground floor should be labeled 0. So indexing in Python starts at 0. So I'm looking at the first tree, right? I'm pulling out the trees that this estimator has fit. I'm looking at the first tree, but it's always indexed by 0 because we're in Python. And what is that first tree? Well, it is a decision tree classifier. So it's one of these flow charts of where you answer yes or no. And then there's a lot of other parameters here that we didn't even touch. We don't have to touch until we really want to fine tune our models. And it's a little bit beyond what we'll talk about today. But by the way, if you wanted to make this same decision tree classifier, you could use this random state here, use that same number, and we'd end up with the same decision tree classifier. By the way, just another place you've seen this random state. And yeah. So let me continue down here. Yeah, good. So we pulled out our decision trees, and what I'm going to do actually is take a vote. We made a sample, and it said that sample was Virginica. Everybody remember, we made up a false sample that I kind of pulled out of thin air. We threw it through, and it said it was Virginica. And let's see what votes there were from those 100 different trees. So what I'm going to do is for each tree in my set of trees, again, there's a little bit of Python class method applications here that we can talk about and we can get deeper into it. I'm happy to decompose all of it. But just for the moment, let me tell you what I'm doing in this line. I'm taking a vote amongst all the trees and asking which each of the trees are voting for. And it turns out that somehow I chose those numbers so specially that all 100 trees guessed class 2. So certainly I will be assigned class 2. It doesn't always happen that way. It could be, say, 3 guessed class 1 and 97 guessed class 2, or it could be, 40 guessed class 1, 5 guessed class 2, and 55 guessed class 0, and whichever one wins, gets the vote. But you could imagine, each of these, you can imagine it saying 0. The label of 0 got 0 votes. A label of 1 got 0 votes, and a label of 2 got 100 votes. It's just magic right now, but I can make that into probabilities as well, right? So I can just look at the fraction. So let's just say, unfortunately, this example didn't work out as well as we had hoped, as well as with a royal we. I wish that there had been other trees that voted different ways, but for the moment, if it was 97 that voted 2 and 3 that voted 1, then I would say 3% probability of it being 1 and 97% probability of it being 2. And what's nice about that is my random forest can tell me what those probabilities are. It just so happens that all 100 voted for Virginica, and so the probabilities are 0 of Setosa, 0 of versicolor, and 100% or one probability of 1 of being the Virginica. So what? Well, it's just cool that we can look at this as a probabilistic classifier as opposed to just a yes or no. You could think that maybe you can get some more information out of the probabilities. It tells you about the decomposition of the votes of the trees rather than just a yes or a no. Is it Virginica or not? And so there's extra information hidden in here, which is quite useful, which is the point of me showing you that even though it seems a little bit afar from what we were talking about. And so, of course, you remember my Da Vinci masterpiece of the beer, wine, or cake. Here is one tree's actual, the one tree's actual chart, I should say, right? So this is if I create a decision tree classifier for the iris data set, but instead of using all 4 features, because that will make a much longer tree, I'm just going to use 2 features, and we see how it breaks apart. So I'm just going to use, say, sepal length and petal length to create one decision tree classifier. And so x0 here will be sepal length, x1 here is petal length. So what this first cell says is, hey, is x0 less than 2.45? If yes, we'll come here. It turns out that if your sepal length is less than 2.45, well then you are definitely Setosa. Setosa is very easy to classify. It's actually quite far removed. But if you are not, if your sepal length is greater than 0.45, you have to go this direction. And then the next question is, okay, well, you have a sepal length greater than 2.45. What about your petal length? And it's like, okay, well, maybe if your petal length is 1.75, we go this way. If it's greater than 1.75, we come this way. But look what happens. So there was 150 samples, if you remember. There was 50 Setosa, 50 versicolor, and 50 Virginica, right? By asking that first question, we were able to peel off all the Setosa. And now we only have 50 Virginica and 50 versicolor. We asked the next question about its petal length, and depending on where you land, we've almost done a great job because 49 of the 50 versicolor land on this side, and only 5 of the other one land here, versus 1 of the versicolor and 45 of the other here. So we've done a pretty good job already at this cut. This decision tree is doing quite well, but we can keep going, and we can keep going, and we can keep going, and eventually we divvy up the rest of those 100 different samples into being this final leaf, this terminal node. If I follow all the paths and I end here, well, I'm definitely going to guess versicolor. If I followed all the paths and I landed here, well, then I'm going to guess Virginica. If I followed all the paths land here, I'll guess Virginica. And if I followed all the paths here, Virginica, and here, Versicolor. Right? So this tree keeps going down until you've hit some criteria, which is, again, another parameter for you to choose and something that we can use to fine tune our model. Nothing that we have time to talk about before the question and answer session and we all get free to have more pizza and beer. But this is just something to think about. This is what's happening in this decision tree. And now our random forest went in and made 100 of these decision trees, and each of these hundreds have paths that each sample follows down, and each of those paths get a vote. Now, one thing I want to make clear is the random forest worked pretty well in the iris data set, but almost everything works pretty well on the iris data set because it is such a nice and easy visual data set to use, and it's good as sort of like as an example data set. But I want to use a more realistic data set and one that actually is more complicated, because a random forest, by making all these decision trees and taking a vote from each of these decision trees, it's a pretty complex model, and it's actually applicable in many, many ways. One way that we've used it for is with handwritten digits. So there is a very now famous data set of people's handwritten digits 0, 1, 2, 3 up to 9. And what we want to do is take a picture of a handwritten digit and guess which number it is. And of course, this is from life, because when you get mail sent to you, there's not a mail person behind everyone writing down the address to go to. It goes through a machine. The machine scans the address. Most of those addresses are handwritten. And it has to discover which numbers that those handwritten digits are using and which letters. And then it divvies it up itself, as opposed to somebody having to do it by hand anymore. And so, this is something that's sort of applicable in real life. And I'm going to read in a very big data set. So this data set has 45,000 samples of handwritten digits. And then, that's actually not quite right. There's 70,000 samples of handwritten digits, but we're going to train on 45,000 of them. And then we're going to see how it performs, not on those 45,000 again, but on another 10,000 that it's never seen before. Because that is really how we want to characterize our classifier, right? We don't care if it can tell us things that we already know. We care if it can tell us things we don't know. And so I'm going to create a training test and a testing set. Right, so starting with our training set, I read in my training set. Let's run through this real quick. I have a CSV file saved, the comma separated value file saved, where each row of this is 1 pixel's value of color. So you can think of this as grayscale. So the bigger the number, the darker the image is, up to 256, right? 0 to 256. Say at 256, you're at black. At 0, you're at white, or vice versa. But we have a 28 by 28 image. Each pixel within that image has a particular gray number associated to it, and each of those images have been flattened out into a 784 long row. So we consider each pixel in this image to be a feature. Before it was sepal width, petal width, sepal length, petal length. There are 4 features. Now there are 784 features in this. And just to, let's see if I can do this, make it actually show. Just to show you what's going on here, again, I have the data, which are the pixel, concentrations of gray, and then the actual target, what those numeric values were. I look at it and say the first 3 values of the first 3 true values are 7, 4, and 9. So the first handwritten digit should be the number 7. For those online, let's make sure you can see it. That's what it looks like. Maybe a 7, but it's supposed to be a 7, right? We could do this for the 4 and for the 9 as well, just to give you a feel for it. There's the second example that we have, a 4. The third example will be a 9, right? And you can imagine that it's not so easy to read handwritten digits on the fly. It's sometimes handwriting has a big deal, but let's see how well we can teach a computer to do it. And I'm going to do it like I did before. This time I'm not going to swamp that poor website's server, but instead we'll do it here. I'm going to create a random forest classifier again, just as I did before, I'm just going to call it RFC2 so we don't destroy the beautiful iris random forest classifier we made before. And I'm going to fit it now on that training data and the test set, and the training data and the training target. Everybody remember? So I have my new random forest classifier. I fit. Here are the measurements I can take, and here's the answers I want it to produce, right? I'm going to look and see if I can find the structure in my measurements to reproduce the answer. I do this. This actually takes a little bit of time, so it's already compiled, thankfully. Because if I actually hit .fit now, then I have to try to think of a joke for you guys over the next 2 minutes when it's fitting, and we don't have that much time until it's Q&A anyway. But I do this, and then I look at my score. And if I look at the score on the set that I trained on, I do perfect again. My classifier looks like it did pretty well on the training set itself. But to a certain extent, I only care a little bit about how well it does on that training set because it already knew the answers. I want to see how well it does on something that it didn't already see, how well it does on a test set, on a set of digits that it hasn't seen yet. And so I'm going to read in new data that it has not been tested on at all, that it did not use in its training. I read in these new values, the X test and a Y test. So this is new set of measurements and the correct answers for it. And I can look at the score in that case, and I get a 96%, 97% accuracy. This is still quite good. It is much, much, much better than randomly guessing. And so this random forest classifier still did quite well. So 96%, 97% of the time or so, we can be pretty confident that we are getting the correct guess of a digit. And I just, for those at home, I know I'm looking at you now. There's cheers. I think some people are actually crying from happiness. Yeah, it's pretty incredible that we have this success in a few minutes from creating this classifier with handwritten digits. This is something that, even 20 years ago wouldn't have been quite so easy. Even 5 years ago wouldn't have been quite so easy. And just for fun, I wanted to look at, there were, in that test data set, by the way, there were 10,000 new samples that had never seen before. Of those 10,000 new samples, it missed 326. That's still 326 wrong. We could fine tune that model and get it much better, but we won't do that now. And let's just look at some of the shapes that it gets wrong and what it's guessing. So here's a shape. I don't think it's so hard to guess that this is a 4, but our machine, because of whatever's going on in those decision trees, most of the guesses were that it was a 1. So it misclassified this one as a 1. Many of the ones that it misclassifies are actually 9s. Let's see if we can find another one to show you what it looks like when we miss. There's another one. This is a 2, is my guess, but it was misclassified as an 8. But just imagine thinking as a computer, this kind of looks like a bulb here. This kind of looks like a bulb here. So it's not that far off in terms of pixel density, because now all you get to see are the actual colors on it. And it looks like could be a bulb there, could be a bulb there. So it doesn't actually, even though it's misclassifying, I don't think it's misclassifying terribly. It's sort of misclassifying sensibly. And if we had the time to spend here to look through all the bad examples, there are some that I still don't know what they are, right? It's a very creative type of handwriting. So finally, I won't compile that all. I know it's time for Q&A, but let me just mention one thing. So we know why it's called a forest. We know that it's called a forest because it takes many trees, and each of those trees gets a vote, and because it's composed of many trees, it's called a forest. But why is it called random? Well, the reason it's called random is because, well, this is twofold. One is here we had 784 different features. What it will do is it will randomly select 10, 20, it's up to us to choose, maybe 10 features to create the tree, and then randomly select a different 10 features and create a tree, randomly select 10 different features and create a tree, because we want these trees to be different. If we kept reproducing the same tree, this result will just be the answers of that one tree, right? Or if we kept creating trees that are very similar to each other, it wouldn't be that interesting. So random forest, what it does is say, I want to create a lot of different trees. A lot of different trees that see a lot of different types of data, so that each of these trees has some impact on this model in a way that doesn't, gives me different information than this tree does. And so it randomly selects certain subsets of those columns to then put together an answer. So that's one way it's a random forest, is because each of the trees is built randomly on a, on a random selection of the columns. But it's also random because before it decides to make the tree, it takes the rows of those selected columns and it shakes them up. So each of the data sets look a little bit different also. I mean, they're real. It doesn't change any of the answers. It just changes which ones that our tree sees in its decision-making process. And so these two different dimensions of randomness are going on in this forest so that our trees have different information in each of them, and then each of them contribute an answer in a way that actually helps with accuracy more than just one tree would. And that's a overfitting, underfitting conversation that I would love to talk about over a beer. All right, so thank you guys very much. Let's see, are there any questions for me before I hand back to Pranjali?
Very quick question.
Yes.
We have one example that this misidentified, this is 2.
Yes.
So it's showing an 8. How do you teach back to make it, this is really 2? Maybe it's kind of fundamental.
So, no, it's an excellent question, right? Like there are a few techniques that we have, right? One of them is we see that this didn't perform as well as we wanted it to, right? It's missing some of the ones that we don't want it to miss. We can go back into a lot of those parameters. Say we can increase the number of trees. We can make a different cutoff. Remember, there's like a probabilistic cutoff. You can say maybe if here between a 2 and an 8, the probabilities were quite close, right? It maybe was like 55% 8 and 45% 2, and so we might make a different cutoff for the probabilities, saying we're missing a lot of 2s as 8s. Maybe we'll say if it is 45% likely to be a 2, we'll guess 2 just to try to capture them. But there are several ways and several techniques, and there's not like one size fit all way, but there's several techniques to mitigate these misclassifications. Yes. This is publicly available, yes. This data that we use for this section is what's called MNIST. It's the MNIST data. It is handwritten digits. Jean LeCun, who is the, I think, AI, the head of AI at Facebook, is one of the people that has worked on it since, I don't know, since it's been around, and it's hosted on his site. But also for those who are interested, if you have some deep learning knowledge, there's TensorFlow provides this freely available in their, I don't have it written here, but TensorFlow also provides it in their Keras API, which is easier to grab than the one online if you have TensorFlow with the Keras API ready to go. Okay. Other questions? Yes. Okay. So the question is, how does the machine know how to create the tree from these different features that it has? In this case, in the handwritten digits, there's 784 features because there's 784 pixels and they're 28 by 28 square. So each of the colors in that pixel is just represented by a number. And we want to say, hey, how does it know how to do that? And the answer is going to be similar to a lot of machine learning answers that you'll get for that similar question. We have a cost associated to getting a wrong answer. And what we do, and I'm actually happy to sit down with you on a piece of paper after this, but what we do is based on that cost, right? So we try to make a split on, say, the first feature. We try to make some splits on the second feature. We try to make a split on the third feature, and whichever one lowers our cost the most, we take that split. And now we look at that split and we divide it up into 2 new subtrees, right? And then we ask which feature at which cut point reduces our cost the most in this subtree, and which feature with which cut point reduces our cost the most in this subtree. And then we keep following it down until we've hit some sort of tolerance of how low we're willing our cost to be, for example. And that is how we make the decisions along the way. But at the end of the day, there's really some sort of cost, some sort of penalty for getting a wrong answer. And we're always trying to minimize that penalty. And it does the same thing here. Does that answer the question? Unsatisfactorily? Yeah, okay, good.